Thanks very much, Jane. Good evening, everyone. And where's the camera? Hello to the people who are watching online. So I tend to wander around normally in lectures, but for this, I'm going to stay here so that I'm captured on the video. So as Jane said, my name's John Orr. I'm a university lecturer in Cambridge. I'm a fellow of Magdalen College and the PI on this project, which is Minimising Energy in Construction, what we call MEICON, as a brief acronym. And really the purpose of this evening's lecture is to present some initial findings of a report. You might have seen a link to the report on the website and the emails that were sent around by the institution, but really to begin a conversation with structural engineering about this topic, about energy, about embodied energy particularly. We've undertaken some work. It's the beginnings of the project, and we have lots of questions which we hope collectively we can answer together. So the structure of the evening then, we have three parts. Part one is me. I'm going to talk for about half an hour, and then Chris will cover the industrial part, and then we'll have a discussion and a Q&A. And for the people online, there is going to be a method by which you can ask me and Chris, or anybody, questions. So we're going to try and bring in some outside perspectives as well. Okay, so for the next half an hour, roughly, I'll give you a bit of an introduction and some context to the MEICON project, talk a bit about the vision that we have. As I say, I just repeat myself, it is the beginnings of a conversation, it's the beginnings of a project. I'm going to talk about a survey that we ran last year. Many of you may have submitted your answers to that survey, for which I'm hugely grateful. It was anonymous, so I can't thank you personally. I'm going to go through a few results and then some analysis, and deliberately not really any conclusions. It's lots of open questions. So the context of the project then really goes right back to climate change and looking at things like COP21. COP21 sets out this ambition for a 1.5 degrees centigrade limit on temperature rise. And in the UK, that manifests itself as an 80% reduction in CO2 emissions. So that's just for the UK. Obviously important around the world. Global population is going to be 9, 10, 11 billion people by 2050. Most of those people, 68%, will be living in urban areas, so we have hugely increasing urbanization. And that's really important for the work that we do as structural engineers, because about 40% of energy-related CO2 emissions come from buildings and from construction. So it's important environmentally. The sector is also very important for the economy. So 10 trillion, that number is. $10 trillion is the global construction sector, roughly. So it's about 13% of global GDP. And in the UK, the figures are slightly different. So it's 8% of UK GDP, roughly speaking, 10% of jobs in the construction sector. So it's really an important part of our economy, important part of our environment, and the things that we do underpin and other sectors which make the workers have places to go, modes of transport, all of those things are really fundamental. So despite that importance, when we talk about the economics of the industry, you might have seen something like this. You might not have seen this slide before, but you'll have seen something like it. This is productivity, value added per worker. In the period from 1995 to 2011, data from 7 countries there, construction productivity flatlining, while manufacturing nearly doubles, so 1.7 times. So we have a huge challenge there in dealing with that productivity, whilst also satisfying the economic and the environmental constraints. In that same period, if we were to look at energy use in the buildings that we create, the energy demand balance has really changed. So there's been huge changes. So maybe 30 years ago, if you were to analyze whole life energy use, a significant proportion of it would have come from operational energy. So the lighting, the heating, running the computers and so on. We've decarbonized the energy supply, we've got better installation, we've got better energy efficiency in appliances, and we've had a huge number of directives and requirements in energy performance, such that the pendulum, if you like, has kind of swung the other way, and you can now have buildings with very, very low operational energy, in almost zero. Not quite zero, but almost zero. So it's swung the other way in a well-designed structure, which makes the embodied energy as a percentage the more important thing to consider. Okay, so now we have to tackle embodied energy with the same vigor as we tackled the operational energy. And so this is actually an example now, 7 years ago, 2010, 8 years ago, sorry, a 60-year life cycle of a structure in London, 70% of that whole life energy coming from the embodied energy. And it's the embodied energy that structural engineers get their hands on. It's the materials, it's the stuff that we have some impact, or a real big impact on. As an example, this is a case study in London, tall building. 79% of the initial embodied energy comes from the substructure and the superstructure. Another study from Catham and Burridge, 70% of the initial embodied energy coming from the substructure and the superstructure. So a large portion is in your gift as structural engineers. So far, perhaps no problem. We need bridges, roads, infrastructure, offices, places to go, places to work. That's part of modern life. We want these tall buildings. They require concrete to put them up or steel to put them up. One problem comes when we look at these structures and say, well, how effectively, how efficiently are we utilizing the materials? How are we using this embodied energy? It has a big impact on the environment. Are we actually making good use of it? And you might find, there's two studies down the bottom, 50% of that material is, in inverted commas, wasted. And that's a real concern. And it's a particularly big concern when we look at this report from the United Nations, where we expect to build, in the next 40 years, 230 billion square meters of new floor space. Okay, so huge amounts of construction. That won't be happening in the UK. That will be happening in other countries. That's like building Paris every week for the next 40 years. So this is the kind of scale of the challenge, right? So all of those things I've just said, lots of data and statistics, add up as like a combination, which you could either say that's a perfect storm or a huge opportunity to do something really amazing with the materials that we have. And just a final point about other countries is that 230 billion square meters, 100 billion square meters will be built in countries without any mandatory building energy codes. Okay, so for us and for the institution, there's an opportunity there to show leadership in how this could be done to the best effect. Which leads us to this project. So, Minimising Energy in Construction, funded by the EPSRC, to whom we're enormously grateful, of course. It's a relatively short project. It's only 2 years, and it's intended to be a feasibility study. That's the whole point. It's the beginnings of, hopefully, millions of pounds, not hundreds of thousands of pounds. And our long-term vision is to make this idea of whole-life energy consumption using minimum material resource the guiding principle for design. Okay, that's our long-term vision, maybe several decades away. The immediate ambition in the project is to use feasibility studies to address and identify and address these sources of what we're calling wasted embodied energy and value-less cost. And that really fits in with two key documents, which I'm sure you've all seen and read. The first of which is from 2013, which is Construction 2025, and there are 4 main targets in this, 2 of which are important for this presentation: to reduce costs by 33% and to reduce carbon dioxide emissions by 50% by 2025. Okay, the other 2 relate to the speed of delivery and the trade gap. So that was 2013. Much more recently, we've had the sector deal for construction coming out of the industrial strategy, and that talks about transforming construction for all the reasons I've just outlined, and focuses then on digital, on off-site, and on whole-life performance. So these are really the key things that we and the government want to be able to achieve, and there's £170 million in the Industrial Strategy Challenge Fund to deliver on those ambitions. So the project team is made up of myself, Mikhail and Jamie in Cambridge, and Alex, Stephen and Tim in the University of Bath. We're supported by a steering committee. I didn't count how many companies there are, but it's chaired by Expedition and Chris, who's going to speak in a little bit. We are always open to new discussions, collaborations. If this is interesting to you, just let us know. You can either email me or go to the MEICON website. We want to engage with as many people as possible to try and make a positive change. So, as I say, I'm going to talk to you about the initial things that we've kind of done already. We did a survey last year, 2017. The purpose of the survey was to examine the current culture and practice in structural engineering design as it relates to embodied energy. Okay? And it ran for a number of months, 36 questions, completely anonymous, although people could leave their names if they wished. There were 7 sets of questions, various areas that we wanted to look at. We're not going to go through them all tonight. We're not going to sit and go through them all. There were 129 submissions in that period, August to October, and that's a significant enough population to make us quite confident in these results. So we can do analysis on the numbers of people, but with a 95% confidence, then we have a margin of error of about 8%, which makes no assumptions about skew of responses. So that's kind of the worst case assumption. And it's just important to note that while 129 sounds small, you don't need a large number of people if your population is very big. That's how telephone surveys work. And when you get rung up and there's a survey about who's going to win the next election, they don't need to survey 200,000 people. They survey a very small number. So we're quite confident in what's been found, although, as I said, we're always open to more submissions, more contributions to these questions. I have a prop. Behind me is all of these copies of the report. I don't know if there's enough for one each, but certainly at the end you can come and take a copy. This has all of the questions and all the responses. And crucially, it has all the new questions that we're asking. We've divided them up into industrial questions and research questions. They're also online on that link. And there's an academic paper which you can also read if you wish. And really, it's just a call to say, please engage with what we are considering. So who answered the survey? The population, mostly structural engineers, mostly from the UK, mostly men, a wide range of job titles, I suppose, wide range of experience. And we compare in the report this population with the wider population of engineers in the UK, and it's a good sort of subset of people. So we can treat the results with quite a lot of seriousness. So I want to jump straight into the questions. So for those who didn't do the survey, I'm going to explain what we're going to see. This is question number 1. It's a Likert scale question, and that means you're asked this, you're given this statement, and then you choose between strongly disagree and strongly agree, 1 to 7. So it's going to come up in a second, and I'm going to plot the responses here. So we asked the respondents, maximizing material utilization is a key design criterion for me. 81% on the 5, 6, and 7, so the agree, medium agree, and strongly agree, which is very positive. 12% neutral, not many people saying strongly disagree. Okay, so that's what you're going to see, a few of these plots. 1, 2, 3 is on the negative side, and 5, 6, 7 on the positive. But then we looked at kind of the drivers behind why we see wastage in real projects. And question 8, 9, and 11 looked at those drivers. So question 8 was saying, does your client or your design team require you to minimize embodied energy? And now we have a scale of never to always, and we see it's on the other side. So 70% of people saying, not usually am I required, or never am I required to minimize embodied energy. Do you present material utilization to your clients? The numbers are almost identical, with a slightly heavier skew towards never. 70% saying, we don't present this to clients. And do your clients insist on low carbon designs? Again, very similar numbers on that side. So people aren't asking for this thing, so therefore, perhaps, why would you do it? If you're not being asked, other pressures dominate. And one of those other pressures which we've extracted from the survey could be the construction site. So in question 4, we said, do you agree or disagree with the statement that an easily constructed structure is more valued than a materially efficient one? And 80% of people agree. My design team would rather it's easy to build than materially efficient. And 60% of people think that, or agreed that, the potential for errors on a construction site influences your sizing of members. So the sizing's got nothing to do with the structural utilization, the capacity, it's the potential for it to go in the wrong place in a construction site. And overwhelmingly, 95% of people say I simplify my designs to improve constructability and make things simple because I don't know what's going to happen next. So there's all these other pressures, whereas we started at question 1, yes, I would love to have material efficiency, but actually X, Y, Z things happen, and perhaps we don't have material efficiency. Does anybody know where this is? If you've ever seen this factory before, this is a Tesla factory, so in America. It's indicative of many car plants, of course. Part of transforming construction could be, I would put it as a question, could be that we shouldn't need to simplify, that mass customization, which is done in the manufacture of shoes and cars and aeroplanes, should be part of the construction sector. And the Transforming Construction initiatives are trying to bring in the automation that we have in other sectors into construction. Construction is still very far away from this being how you build a building, very far away. But there's a question as to why is that? What is the key driver for that? And there are research projects in the automation, in the robotics, which are going on at the moment. And so, as I say, in this report, we highlight a whole load of questions. I think there's 36 questions, and I'm not going to go through them all. But that initial bit led to a key question, research question 1, which is saying, how do we align the incentives of all those various people, clients, engineers, architects, legislators, contractors, so that the preferred outcome of every project, not just one project out of 100, but every project, is minimum embodied energy or minimum environmental impact. And there's some associated questions about, can we define benchmark values of what should we be aiming for in embodied energy? Can we find a way to present this to clients so that they understand what we mean and what the importance of it is? And how do designers demonstrate, or how should they, or how could they, demonstrate they're meeting the Construction 2025 targets? So what are we doing to make sure that we show this? And so in the context of benchmarking, on the left-hand side, you've got a picture which you might recognize when you buy a fridge or a washing machine. So this is actually for a building, which I have made. So you've got your energy rating, your embodied energy rating. You've got the size and the shape of the building, the location, what type, how many years you're considering. The A and B is kind of the scope of your assessment. And so perhaps we need some way of measuring this in a consistent way. There are tools which I'll talk about in a second. But then we raise all sorts of questions like, what is an A-rated embodied energy building? What does it look like? How do you present that information? Does anybody really know what kilograms carbon dioxide equivalent per meter squared means? People might understand pounds, but perhaps not other units. And how do you enforce this? It's not as if people pay every year for their energy costs. The embodied energy is a thing which happens at the beginning, and the impact is much wider than one person. So perhaps planning permission is a way in which embodied energy can be minimized. And what are the boundaries to your measurement? I'm going to come to 15978 in a second, which you probably have seen, but there's a whole number of ways to skin the cat in measuring whole life carbon and whole life energy. And crucially, what number do we choose to meet those climate commitments? We could set a benchmark of 2,000 kilograms per square meter, and we would massively overshoot on 1.5 degrees centigrade. So this is a real challenge. And there are a huge number of codes, tools, techniques, assessment methods for measuring carbon. EN 15978 is where this figure comes from, and you've got all the various stages of your building, A to D, and so in my diagram, that A plus B means we're considering production, construction, and use, but nothing else. So you draw your boundaries. This is starting to be picked up. So if you're a member of RICS, then you may well have seen this document, the Whole Life Carbon Assessment. So it's written by Simon Sturgis, a group chaired by Simon Sturgis, really great document. And it's now mandatory for RICS members to undertake a whole life carbon assessment of the substructure and the superstructure across those 7 areas which are highlighted in red. So this is becoming a tool, and at the moment, this is a tool to count, effectively, to measure how much embodied carbon is in your structure. And people have done this, of course. So there are plenty of databases which exist. This is one from 2017, Simonon, I think it's Washington University. So you've got 514 commercial offices, and we're plotting the median as 400 kilograms per square meter. But there's one out there, 2,700, which is an outlier, we will say. And this kind of highlights limitations in these methods, that the data inside these 514 have been generated in a whole variety of different analysis methods. And so how do you compare them? So 2,700 might actually be a better, in inverted commas, building than the 400. How do we know what to do with that? And then crucially, as I said, in benchmarking, where do we draw the line? What is our target? Is the target 2,700 or is the target 10? And what should we be aiming for in terms of a pathway to minimum embodied energy? So that's the question about improvement. How do we actually improve? So the first thing is to measure, to find out what we're doing, but measure in a consistent and comparable way, and then somehow set benchmarks. And who sets the benchmarks? What is the benchmark targeting? And as I said, that could be potentially planning or legislation. And it possibly involves a change in design philosophy and culture, in that we have to critically examine design and say, okay, we've done this, but we can do X, Y, Z things better, and be willing to tell clients, the public, what you're going to do, what you're going to change, which might entail some commercial risk for companies of being open about the data that we collect. So, talking of risk, I'm going to now move to a quick thing about loading, which is part of everything, part of every design that we do. This, of course, is the Golden Gate Bridge, 1987, 50th anniversary. They allowed people to walk over to celebrate the anniversary. There were 300,000 people on the bridge, so that equates to about £60 a square foot, 2.9 kPa, so that's a huge crowd of people on there. Could be the most extreme load it's ever seen, I don't know. They were certainly worried about it afterwards. And so in the survey then, we asked people to imagine, in this loading context, we asked them to imagine you're designing a tall building, repetition of floor plates, so 50 stories. Tall building, and we asked 3 questions just to get a feel for where we are. So we asked, what would you use as a design characteristic load? And the median value was 3, but it was a range from 1 to 10, so that's interesting. The average in-use floor loading, so average in use over 60 years, 1.5. So remember, characteristic is a statistically extreme value, and average in use is the average value. And then we said, well, what would the maximum be over 60 years? And that came out as 2.5. Okay? So just to kind of highlight this, the average in use 1.5 is 6 bags of cement per square meter on average. So sometimes more, sometimes less, but on the balance, it's 6. So that seems quite high. And this is possibly something you've all heard before. Design codes say 2 to 3 kilonewtons per square meter in Europe. London is maybe a bit weird, but London has a sort of historic practice of using somewhere between 3 and 5, if we look at real buildings, real constructed buildings. But we know that the real loading, the actual loading from the people and the furniture and the stuff, is somewhere around a tenth of that, so 0.3 to 0.5. And we've known that really since 1893, so that was the first one that MEICON did a really good survey of where these data come from, and 1893 was the first. And then the Stanhope was Fitzpatrick, and Mitchell and Woodgate, the BRE. So there's this kind of disconnect. And back in 1925, this author was saying that, we've looked at live loads, and there's no real basis for it. It's tradition, effectively. There's no scientific basis for it. And from skipping forwards to 2014, the BCO Guide to Specification, I think I can quote from this, says, buildings designed for far higher than regulations require, based on a perception in a marketplace. And a perception in a marketplace driving loading might seem odd, whereas perhaps when you were at university, you were told that this diagram is true. I'm not going to go through the diagram, don't worry. This is the overlap between load effect and the resistance of your structure. And you say you've got some distribution, statistical distribution of both of those things, load effect and resistance. They overlap over here. You do a convolution integral. You can work out all sorts of things. But what if the green is so far away that it's not actually something we can do? Does that actually mean anything? And so that idea about tradition, historic practice, is in the Eurocodes. So I'm just going to put a piece up from the Eurocodes talking about psi factors and partial safety factors, the basis for which is the calibration against a long experience of building tradition. That's where they come from. They don't come from a statistical thing. They're the calibration of a long experience of building tradition, and as it says, that's the leading principle for most of those factors. And that contributes to, because we're always calibrating against historic practice, it contributes to what we call perhaps a one-way ratchet in codes, and that it's very difficult to go the other way, to start to reduce things, because we don't measure, we don't have enough data to support those decisions. And so we are kind of trapped almost. And that led to a series of questions about what should the envelope of floor loading be, what would the benefits and consequences be. We have to be very conscious of the potential for unintended consequences of changing these numbers. That's really important, but based on measured data. So when we start to measure things, can we actually inform practice to improve practice? And I'm going to take a slight deviation. People have been measuring buildings for a long time. In fact, the Baker building where I work was built as one of the early plastic steel frames with strain gauges installed on it. But I don't know if they were ever connected to anything. I'll have to find out. This is the new building in Cambridge. It's part of the UCRIC funding from the government, and it's the National Centre for Smart Infrastructure and Construction. There's about £500,000 worth of sensors in there, not just strain gauges. What they look like in reality is things stuck onto steel beams. Okay, that's literally what we do. We're going to stick them on, and we're going to measure the performance of the structure and interpret this in some way. I asked one of my colleagues for a plot. So this was in March. This is the kind of thing you get. You get a plot of the change in strain, right? So you get some data out of it. The lines don't matter. The important thing is, if we're going to say we want to interpret something from the built environment based on data, based on measurement, to increase certainty, then we're dealing with lots of information potentially. And the difficulty then is, how do you get this bit, the red dot, how do you get the insight out of all the noise of strain gauges in beams or vibrations in floors? And how does that inform practice? It's very, very hard to see how you pick those things out. Otherwise, we end up with a measurement system which plows out loads of graphs, but does that impact your design practice? What would you need to see? And the more things that you measure, the more correlations you can make. So there's a website called spuriouscorrelations.com. So we can correlate with 95% certainty United States civil engineering doctorates between 2000 and 2009 with per capita consumption of mozzarella cheese. So they are identical. 95% correlation absolutely means nothing. So it's easy to do this if we collect lots of data. So we want to introduce certainty, but we have to be aware of the limitations of doing that. And so the question might be how best we do that for bridges, for floors, for office buildings, for ultimate limit states, and for serviceability limit states. That's a real sort of challenging question to deal with. And so the final part of my section is to talk about serviceability. And we asked in question 20, how often does SLS govern your design? Okay, so how often are you governed by SLS? And again, going back to our Likert plots, we have 91% of respondents saying that's how often. 91%, it's more often than not that SLS is governing the design. Question 22, so only 2 questions later, said, how frequently would you be comfortable with these SLS limits being exceeded? So again, we're talking about an office floor, and we divided up into various categories. So for deflections, people were happy with deflection limits being exceeded the majority of the time, 10% of people, 20% said never. For vibration, only 2% said that could be exceeded the majority of the time, 30% said a few minutes per day, 10% said never. And for cracking, so we're talking about concrete, 10% said the majority of the time, but 40% said never. Okay, so this is kind of interesting in itself, that a large number of respondents and the population are happy for SLS to be exceeded occasionally, which is intriguing if that's what's governing your material use. And so to illustrate why that's important, this is a figure from Cyril Dunant in Cambridge. What you're looking at is 3,600 beams in real buildings. We have the utilization ratio of each member on the x-axis, and then the mass fraction on the vertical axis. The first thing we can note is there's a peak around 80%, so people are working to utilizations of around 0.8, and then the obvious question is you're missing out on 20%. Why not work at 1? But the other interesting thing is when we look at what's in these grey bars is the governing criteria. So 60% of those beams, that sample of 3,600, odd, I think it was, are governed by SLS, but we're happy for that to be exceeded. So how is that? Is that something we are actually happy with as a set of designers? And would we instead want that plot to look more like that, where most of the mass is being used to a high utilization ratio, and in that plot you've not changed anything about the design codes. They have stayed completely identical to they are today. But instead of being governed by SLS and having a utilization of 0.2, everything's up at 0.9 and 0.95 and 1. Now, that's possibly impossible. I don't know. I just drew this on my computer. So that's, we can draw anything on a computer. So this is a question. And the question might be, what does that mean in energy, in weight, in cost, in construction? What does a building that looks like, has that result, what does it look like? And it's very likely that you do need a percent of mass down at these utilizations for those extra bits of steel that don't really do much, like the trimmer beams and so on. And that might be 6% of the mass of the building. But why not make the bulk of it shift towards the right? And then finally, we asked people, you're designing this multi-story building floor plate, what's the biggest influence on your design? Okay, what really concerns you? So construction ease, as we said before, we've seen that already, that's important. 30% saying construction ease. Cost to client, 54%. So people are governed by that cost to the client. There were 2 others. And then material consumption, 20%. So only 1 in 5 saying that's what's really the biggest influence. And it's the cost to the client which people are worried about, and that's absolutely understandable. It's easy for me to stand here as an academic without a business to run and say, that, why aren't we thinking about the planet? But why aren't we thinking about the planet? Because if the cost to client is governing, and that means you're using twice as many cement trucks, then the cost to the planet is pollution from diesel trucks, cyclists getting hit by these diesel trucks driving around London. So the influence of your design might be, the indirect influences can be very significant. And so thinking about that in the round is really important. And that just brings us back to the Construction 2025 targets, where remember that it's 33% less initial cost, which perhaps your client is worried about, but also whole life cost. And if somebody is not going to keep the building for very long, we have to consider the whole life cost in terms of money and also in terms of energy. And I wonder if it is a challenge that's as significant as this challenge. And I put this up because I had a chat with Chris, and there's a film out at the moment, the name of which I've just forgotten, First Man. And, you know, in the 60s, JFK said, we choose to go to the moon, and there was no way of doing it. Actually, we can't go to the moon anymore, but we choose to do it. And then so the question is, what do we choose to do? Do we choose to go to 0 embodied energy? And how do we get there? Because that is the pathway to 1.5 degrees centigrade, and it takes us to 0 CO2 emissions. So our budget between now and 2050 is about 600 gigatons of carbon dioxide emissions for everything, not just construction, for everything, if we're going to get in 2050 to this target, 0 emissions per year, which is what the IPCC, this isn't a made-up graph, absolutely not. This is a real graph from the IPCC report. Very recently came out. If you want to get to 1.5, it has to be drastic. That's a cliff edge drop. So what does that mean in terms of our buildings? What do they look like? What changes? What changes for the user, for the designer? And I was reminded of 3 principles which I think still stand, and I hope you agree they still stand, which you hopefully have read this book. It's a fantastic book if you skip over the beginning few pages, where deference to Caesar isn't really relevant anymore. But Vitruvius is saying that all of these things that we do must be built with due reference to durability, convenience, and beauty. And I think that is a guiding principle we can all still agree with. And that's from 630 BC. So, my last point, my last question was, that I'm going to talk about, was number 26. And we said, thinking about your professional practice, which of the following would be the prime reason for an element to have a design resistance that is greater than the design effect of the actions on the element? So what's the reason for not having a utilization of 1, effectively? And those answers can be categorized as we see on the screen, and I'm not going to read them out, but the important thing is that who is responsible for each of those categories? And we can say it's the design team, the structural engineer, the client, the contractor. If we add up the percentages, maybe 40% of that is in the hands of the structural engineer, making the choice about how much embodied energy we use. And on that note, I'm just going to reiterate that this is the beginning of a conversation and that we want to hear your thoughts. And since we've arrived at design, I'm now going to pass over to Chris, who's our resident industrial designer. Okay, thanks, Chris.
Great, very good. That's fantastic. Yes, so I'm chairing the Industrial Steering Committee for this project, but luckily it's steering itself. So, I took this book with one of my partners to a meeting with a developer about a week ago, and we did the normal show and tell because we were trying to get them to give us a job. So we did the normal show and tell and said, these are all the fantastic projects we've worked on, and we'd really like to work on your project, and we think we're nice people, and you look quite nice as well, so why don't we work together? And that went down like a lead balloon. He said, I'm not really interested in that. Why should we employ you compared to all of your competitors? So I thought, okay, I'll tell you what, we'll try this tack. So I got this book out, which is all of the questions from MEICON, And I said, have you ever seen anything like this? He said, what's that? I said, well, it's about how to minimize the amount of material you're going to put in your buildings. And he said, not really interested in that either. I said, well, so you're not interested in trying to reduce the amount of carbon? You're not? He said, no. Are you interested in trying to help reduce the effects of man-made actions on the climate? No, not interested. This chap was a former architect, which probably explains that. And then, I thought, well, I'll ask you a different question. I said, well, what are you interested in? He said, well, we're just really interested in money. So I said, well, if I tell you we could take the principles in here and reduce the cost of your project from £100 million to £80 million, would you be interested? And he said, actually, no. He said, the reason is because we're only interested in how much profit we make. We're not actually interested in the cost of the building at all, because somebody else funds it. We skin the money off the top. So that it's just a little story to illustrate the complexity of trying to get this stuff through. The people who make decisions about things that you might think, and we might all think, are sensible, rational, reasonable, to a developer, and there are lots of them around, common sense doesn't, well, one of them's President of the United States. The common sense doesn't prevail. And right. So therefore, I've been forced to think about this in a slightly different way to the way that John's thinking about it. And so the industrialists on the steering committee feed this into the research community. And I think it's been a very healthy conversation. It's been great the last year or so since this has been going on. So I'm going to start with a tiny bit of context, which is in 1992, you mentioned the Tony Fitzpatrick led study into office floor loadings. They were actually our offices at Arups. And I was the person who went around and measured all the weights of all the things. And the group we were working on were the people whose weights were measured to tell us what the live loads were and everything. So that is 26 years ago. In 2010, when I got the Mill Medal here at the structures, I gave a talk called Enough is Enough, which is about trying to put enough material in, but only enough. And the reaction, a number of people here were probably at that conversation. The reaction basically was everybody in the audience went, oh my God, what are we doing? Oh my God. They've all more or less put their heads in their hands and go, oh crikey, what are we doing? And so that's 8 years ago. We now have, that was things like, if you do a perfect beam rather than a regular beam, you can save 30% of the material, that sort of stuff. So basic, and it was usually done, at that time, carbon was very fashionable to talk about carbon in the world. So everything was done on the basis of carbon reduction. And so we did compare and contrast, a very sort of similar thing, have a look at stadia around the world, compare them. We did them on the basis of carbon, which we converted for the purposes of everybody's ease of understanding to the number of cups of tea you could brew using the energy that you were would otherwise be spending on your building. So 14, to make the bird's nest, you can make 14 billion cups of tea with the energy you use to produce the steel for the bird's nest. And then we converted it into a sort of washing machine style energy rating for your project. So, and we had a velodrome because we were working on that at the time, which we gave ourselves a B for it because we thought we could do better. But, and things like the aquatics at the Olympics, were very, very inefficient. And we thought the bird's nest in China was particularly inefficient. That went down pretty badly as well. So although everybody said that's fantastic, because it was about carbon, nobody really paid much attention. So I'm just going to put up a couple of hypotheses, and so the first one is just for testing. Engineers may need a bit of help in order to change to use the resources wisely. So we talk about carbon, but that clearly I haven't managed over many years to get that embedded with the people that we're working with on a sort of common enough basis to be used in design. No one asked for it, as has been said in the survey. So something else we probably need help somewhere. There is a hypothesis, which engineers are actually in control of their destiny, and therefore they're in control of their resources. But I don't think, certainly from my own experience, and I'm not quite sure how people here feel about it, it's probably not true in practice. By and large, the other factors, and there are many of them in the MEICON survey, appear to take over. So the reaction is, oh, Jesus, it's not what we were hoping for. So a rhetorical question, does anybody important, by that I mean people who commission engineering projects, people for whom we're designing, actually care about carbon at all anymore? And I suspect, well, I don't know, a show of hands, yes? Who thinks yes, people care about it? Who thinks no? Yeah, more people putting their hands up for no. I think in practice, people do care about it because they can see the climate change impact, but they don't know what to do about it. And certainly when it comes to one-off buildings, one-off commissions, one-off bridges, roads, God knows what, construction, I've never heard a client ask for anything to do with carbon. Never. So the other place where there is a lot of wastage is in people making mistakes. So Ed McCann, my partner, and the Institution of Civil Engineers, the structures, and also a whole group of contractors, clients, and consultants have been working for the last couple of years. In fact, Bruce I saw here, who helped put this together in the early stages, doing a lot of the research for it, looking at the sources of error in construction, because some of those have a direct effect on the amount of resources that are being used. So this was in 2016, so 2 years ago. So Ed and Tom Barton from Robert McAlpine, or ex-Robert McAlpine, have been leading that. And there's round numbers, a quarter of the UK's construction budget is wasted. So this is not, you will have noticed it's not carbon anymore, this is money. So it's converted to money because people seem to respond to that better. Roughly a quarter, and it spreads around concrete, some in facades. I mean, the structural engineer has a part to play in quite a lot of that, and a bit like John's slides earlier, it's in the sort of 40% range, maybe more, depending on what you class as structure. But getting things wrong and the wastage that comes from that is significant. So again, I think in total you're talking about something of the order of 20 billion, getting on for 20 billion out of getting on for 100 billions worth of construction every year in the UK is just chucked away. Badly done, has to be done again, all that sort of thing. And you think that's another source of carbon emissions. And we put those two together this in an attempt to persuade. We started with the National Infrastructure Commission, John Armitt, who was the chairman. We went to see him, and we put together Enough is Enough, and this is before MEICON started. Enough is Enough, and Get It Right. I went to see him to say, the 2025 construction strategy has just been published by the government. You are responsible for influencing the commissioning of infrastructure projects. What are you going to do about it? And here's a bunch of possible ways you can do it, which will save, in money terms, something like between a quarter and a third of the total cost. And of course, there's a benefit in terms of carbon reduction, which you don't have to mention because they will go for the money. And he was interested, amazingly. So then we went to see Robert Mayer at the House of Lords. He was interested. We've seen Andrew Wolstenholme. We've seen a lot of industry heavyweights who are interested. And it's because it's been converted to money. So I want to mention in this context as well a lady called Rowan Conway, who is the Director of Innovation at the RSA, at the Royal Society of Arts. And she's just published a report on how governments procure things. It's very good, and particularly with a social context. And if you say dealing with climate change and dealing with the sort of ethical use of resources is something which has a massive social impact and people want to do it, the RSA report is very good. It's called Move Fast and Fix Things, published in July this year. And Rowan's great. She's written this thing. And I'm going to pick out a few of the diagrams later on but this goes into the mix. And I think all of these things, what's really good about this is that, and then you throw in MEICON as well, so that we're here to talk about today. So all of these things are happening around the place. That was a 6-month study. They produced a well-argued, case-studied report. We've got MEICON, we've got Enough is Enough, we've got GIRI, and there are other things kicking around. So I think the zeitgeist is quite hopeful. We might be able to do something. Interestingly, the civils, they were trying to improve communication between engineers and ordinary people. So instead of talking about stress, strain, and all those sorts of things, they started talking about things that were positive. So they chose all these words. They didn't put carbon in there, so less carbon or anything like that, but bigger and faster and stronger and safer and all that sort of thing. But of course, the word they missed was something which is cheaper, which is, of course, what people really want. So again, we converted the Enough is Enough stuff a year or two back to money, and the savings are significant. So if I said there were 18 billion savings from error, on top of that, from improving the efficiency of the stuff we design, and these are just 4 examples from the simple structures, you got roughly 1 billion for perfect steel beams, i.e. ones which follow the bending moment diagram and the shear force diagrams, perfect concrete beams, perfect flat slabs where you don't have loads and loads of concrete on the bottom just weighing everything down. You only put the concrete in the compression zone primarily. And rational safety and materials factors. I don't know if Clement's here. He's not here, who did a lot of this work. In fact, that's his handwriting. Who's one of our guys. You add them up, there's about 3.5 billion there. That's another 3 or 4% of the total UK. And if you then gross that up around Europe, around the States, China, emerging countries, you're talking about really significant numbers with lots of noughts on, like the great big number you had earlier. And the best magic idea is the one that everybody, I've said this so many times I'm getting bored with it, but anyway, you put, what you do is you take the codes of practice and you write the words and do what you need to do and no more. And you put those in the codes of practice. You don't have to change anything, just say, don't do any more than you need to. That's it, 3 words. And every government contract should have those 3 words written in. Just please provide what we've asked you for and no more. Don't go for 80% utilization, meaning 25% over design, actually. Don't go for 3 kilonewtons a square meter when you know that the loads are only going to be between 0.5 and 1 maximum, all that stuff. But even if you were to comply with the codes and just go for a utilization factor of 1, you would take 20% or 25% out of the materials by the admission of the people who responded to John's survey, who have all admitted, we all add a little bit in from time to time, don't we? Because we all feel probably we should do, because we're not quite sure what's going to happen. That's what the codes are designed for, to stop the need to do that, and yet we still all do it. And if you gross that up around the planet, it's just colossal. It's material that's doing absolutely nothing apart from acting as ballast, weighing down things and chucking carbon into the air, costing money. So, why is MEICON significant, which is really what I'm supposed to be talking about? The first thing is it's independent. And there have been an awful lot of... So Enough is Enough was something done from within the industry. So anybody listening to that from outside the industry says, oh, well, you're saying that because you're trying to influence us to giving you work or something. You're doing it for your own benefit. The fact it's independent, that MEICON is independent, is really important because it comes from outside the industry. And therefore we can all quote it. We can say, it wasn't us that said this. Cambridge University and Bath University have done this piece of work. So that's really good. It's research-led and it has a proper scientific, as you will have seen from John's stuff, a proper scientific research methodology. So, i.e. the figures haven't been cheated. They haven't been manipulated to get the answer, at least as far as I know. They haven't been manipulated to get the answer that John wanted. They come from a very high-status research body and Bath University. And, sorry, John. Sorry, Tim. No, Cambridge and Bath have a very high standing in the world of environmental engineering, materials science, so which is significant in terms of influencing. It can be funded. So if you're a consultant and you want to, or a contractor and you want to get research funding, it's very, very hard to get it funded. If you're a university, you can go straight to EPSRC and say, please fund this project, which is exactly what they did here. And then industry can then plough in behind, as all those people that we've mentioned, and then give it if you like, a hard run for its money to make sure that it actually earns the taxpayer's pound that has come through the EPSRC into the enormous pockets and bank balances of the Cambridge and Bath universities. So I think it's really important, fundamentally, because it's an independent research project done in a way that we can all then use for our own, we can point to and say, right, they did that, and we believe it. This is from Rowan's RSA report, and it's a very simple diagram, but it just to illustrate where we are with the MEICON project. So this is how to, her report is on how to commission public projects, and basically, public projects, you start to get some benefit when you deliver them to scale. Huge number of things. So in engineering terms, we're doing loads and loads of buildings, bridges and everything else, we're delivering them to scale. But how to get to that point and how to get people to ask us to get to that point as well, or commission us to do it, is a problem. So MEICON is actually down here at the moment, which is understanding the problem and exploring, the next step actually is to start exploring ideas of what might happen next. There then are a series, at the end of that you might be able to say what the problem is, probably. Then you've got to design some sort of answer. Then you have to test it. And then you start to review the tests, you've got some sort of proven solution, at which point, only then, can you start to roll these things out. And if you've ever been involved with politicians, you know that the last thing they want is for the Daily Mail to have a headline saying, you know, bridge wobbles. Just to take one example at random. So, I think, and we're very, very early in this process. So it's a long journey. In order to get to the point where this comes out into the public world, at a sort of formal commission level, it's a very long time. So I think we can do stuff now on the basis of what's coming out of these studies and what we already know, if we want to. And I'm going to talk about some of those in a minute. But MEICON at the moment is in the formative stage, and it's for the engineers in the room to say, well, could we do something now, and what might it be? What are the key catalysts for change? And John mentioned some of them. The first one is planning approval or building regs. If you don't get planning approval or you don't get building regs approval, you can't make something. You can't build it, or you don't get a Cat 3 check. You can't do it. So we could change the rules. At that point, people would have to respond. And I think the engineering profession would respond really well if the rules changed. For example, if you put "and no more" in to those, I think it would respond. I think that would be transformative. The ability to win government contracts. So if the government asks in its commissioning process for people to do things in a different way, then people will change. Because otherwise they don't get those jobs. And that's 40% of the UK. In the UK, that's 40% of the construction budget is funded by the government. It's a significant number. And the 2025 construction strategy and also the industry strategy, those sorts of things are useful, but they're a bit bogged down in bureaucracy, or in some cases worse. A little bit nebulous. A set of targets. You know, it's great to say these things. We actually sat with Peter Hansford pretty much the day after the 2025 construction strategy was produced over a very nice lunch and said, well, okay, Peter, so that's what you've said the targets are. How do you think the government is going to help us get there? You know, are you going to invest in research? Are you going to say, I've got no idea, absolutely no idea. That's down for industry to sort that out. So at that point, it's for us to sort it out. So they weren't even going to change the regulations. So these things are useful, but I'm not quite sure how useful. What are the key contributors to inertia? So the same, actually, in a funny way, the same things. If you can get planning permission and building regs approval, doing what you're doing at the moment, you'll carry on doing it. If you still get government commissions on the basis of what you're doing at the moment, you'll carry on doing it. And I was going to put the 2025 construction strategy. If you can carry on doing it and just ignore that, you're going to carry on ignoring it. And the one-way ratchet on codes is a big inertia, where the only way that you can tell whether your project is going to work in the long term is by looking back at all previous projects that have been built in that sort of sector and say, well, they were built to a code which had these numbers in it, so therefore, as long as we don't go below those numbers, we can use that as a calibration set for our new set of codes. That's why you can't go backwards with the loading. So then that says you need to have a different mindset as to how you're going to actually design things. And there are huge, this is another one of Rowan's diagrams. You have an idea on the left-hand side, you do some design, you make something. First pass round, it comes up against this massive wall of stuff, regulatory frameworks, procurement problems, the market's not ready. But the one that cultural norms, so the RSA being the RSA, they're into how people, it's a behavioural thing, social behaviour. And in a bubble that's the same size as all the others, media backlash being the thing that is from the political classes is the thing they're most petrified about, or being voted out of office on the basis of something appearing to go wrong. So it doesn't even have to actually go wrong, it just has to be a bad story. So these are huge barriers. So positive stories coming out of our industry are things that people need to enable them to have the confidence to move forward. And this is just a tabulated version of that, but it's a scary list. Media headlines were confirmed in our stakeholder interviews as the primary driver of fear. These are politicians they're talking to when they're doing these interviews. It's terrifying. But of course, we work for these guys. What's the alternative? I think there are lessons that we should be thinking about from other industries where, an airplane is not going to get off the ground and fly from here to America if it weighs 50% more than it needs to. It really, well, maybe it does, but at which point you're in serious trouble. So I think the degree of over-design in the aerospace industry may be less, and it's something for the researchers to have a think about. In automotive, similar thing, because you're looking for fuel efficiency, you're looking for reduction in drag, you're looking for reduction in emissions, all that sort of stuff. I think there are lessons in product design if you think about buildings and bridges and roadways and railway platforms as mass products. There are lots of repetitions around, and if you build one, measure the hell out of it, and then next time build it slightly smaller and slightly lighter, measure the hell out of that, you're allowed to design things by test. That is allowed in most situations. So I think there's an opportunity probably to participate, and it comes down to measurement and knowing what's actually happening in the buildings we're using. No blame culture in healthcare. So there are a lot of, my brother's an A&E consultant. He works on helicopters, and they debrief every time. And if something goes wrong, they don't go, you idiot, it's your fault. They have a debrief directly afterwards, comes out of the military virtually, and they try and work out what happened right then. And you imagine the number of times that happens in buildings or in bridges, where people say, after the thing is finished, honestly, what was good, what was bad. It's very rare to have that degree of honest, open conversation, but we need to have more of that. And NASA, I put NASA in here because the rule in NASA, when you're training to be an astronaut, is to try and make your collaborators look good on the basis that it's a team effort. So that if you make them do their job better and they're trying to do exactly the same for you, you're going to encourage, empower collaboration. And I think if you think about what that actually means in our industry between consultants and contractors, which is set up to be adversarial, between clients and consultants, which is set up to be adversarial. There's massive penalty clauses, massive insurance policies, it's an adversarial thing. So we can learn from NASA in terms of making each other look better rather than assuming the worst about each other, which is what happens. What's another thing that I think is important is to design for performance, not for code. Meaning, you do a proper risk assessment on the loads, on the materials capabilities, on your comfort doing the calculations, all the things that are enshrined in the code of practice, but you do it on a methodical basis and you do it on a risk basis, as you would do. We do risk assessments on all of our projects. So at that point, why aren't we doing the same thing on the codes and the methods we're using? We should be. Because some of the time we're over-designing because the code says so, but actually the risk of us getting it wrong is precisely zero. It's been done 1,000 times before, we're not going to get it wrong. So I think a risk-based but performance-based design I think is really important. And I think that I've said here, we want an open source database. So we want people to, I take the point about the difficulty of data coming from different places, and I made a point a bit later. It's like VHS and Betamax for people who are very old, who remember that. You need a unified source data format, which with BIM, with everybody using AutoCAD and Revit and all these sorts of things, should be possible to get the data into a format that we can all use, at least going forward. You would imagine that would be possible. If it is, then you can start to mine that data properly, knowing that it's been prepared in the same way. So the protocols, I think, that go into that, not on a one-off project basis, but on the basis that that data is going to go into a pool that everybody is going to dip into and learn from, I think is important. And it can be anonymized. And I think, as has been said, but I think it's really important to mention, there should be a different approach to serviceability and strength, because the consequences of a serviceability failure are basically trivial. You know, they most of the time have almost no consequence whatsoever. People don't even realize. And whereas the consequence of a strength failure can be catastrophic, of course. So, and yet we still use the same loads, the same confidence limits, the same materials, so everything is the same. You think, well, what's going on? The only thing we change is the load factors. And it's for most structures. And you think, well, honestly, why are we still doing that in this day and age? And if you were doing it on a risk basis, you would say, well, the consequences, so you do a risk assessment, you look at the consequences of failure, the cost of mitigation, and then you decide what to do about it. That's how you do a risk assessment. Why wouldn't you do that to serviceability? And say the consequences are trivial, the cost of mitigation is very high, so we're not going to do it. I don't understand. So anyway, we designed, in order to help people, we've designed a structural performance app. So here it is, which is good because you can take it outside. It's called iStress. You can put it on your phone. You can take it to the City of London. You can point it at any building or any structure, and you can see it makes it takes a picture of the building, and it works out what the stress levels are in the building in real time. So you can point it and move it around. It tells you the stress levels. This is working at 38% stress, the gherkin. And we can tell that using our gadget. It says you a warning, over-designed by 38%. If we use this app more, and it's available, I'll give you a link to it on the Expedition website. If we use this app more often, it would be embarrassing to go around London and point at buildings and say they're all working at 38% of their capacity. You know, people say, what's going on? Why have you got such huge things being built all over the place? Why are you using all that material when they're actually only working? Well, we can't do it at the moment, but we've got to move to the point where we have enough confidence in what we're doing to be able to demonstrate that to ourselves and to other people and be held to account for it. So last thing is, what could you do? What could we do, actually? First one is, in the codes, they have special workmanship and materials fudges. For situations where the construction quality is special, or the quality of preparation of materials is special. So you can reduce concrete cover, you can reduce materials factors. There are all sorts of things depending on the material you're using. Most of the time, people don't use those. They tend to. I bet the contractors in the room do, but the consultants don't. We should be using them as a matter of course, because most manufacturing and construction nowadays goes into the category of special construction compared to when the codes were written. So I don't know why we're not doing that. That would take a few % off. I think we should be designing with a utilization factor of 1.0000000, and rather than a utilization factor of something else, as John was showing. Be smarter about serviceability, as I said. Calibrate the completed buildings. And it's obviously a longer play and a big research program needed. But in the end, we're not going to move this forward if people don't know how hard or easily the buildings and bridges, roads are working. Use BIM with a standard format for input and output that can go into a data set that everybody can use. It's ridiculous to have different outputs which are not compatible with each other, which then needs to be open sourced. And I would say you only get planning permission if you agree to put your data into the common data pool. The most important thing of all is contribute to MEICON. Answer all the questions. And the last thing is, every time you see anybody who is anywhere near on a code drafting committee or in a commissioning process or anything else, tell them to put those 3 words in the documents that they give to their engineers. and that in itself will take 10 or 20% out of the materials that we're using. So, there.